Hi, my name is Jim, and today we're going to be talking about scientific notation and engineering notation, which are vehicles used in science all the time to represent numbers which are very large and very small, and it avoids the use of many leading or trailing zeros, which would make arithmetic calculations very difficult. So, for example, here let's take a look at the number of electrons that passes a given point in a circuit in 1 second. And that number is 624 with a whole bunch of zeros after it, and I certainly wouldn't want to find out what a third of that would be by doing, say, a long division on that particular number. So an easy way to do that is to convert it into scientific notation. Now, having said this, many electrons passing a given point in 1 second is the definition of an ampere, and that's a rate of electrons per second. Okay, so to convert to scientific notation needs 2 steps that you need to be very familiar with. And the first step is to move the decimal point so that only one non-zero significant digit is to the left of the decimal point. And the second is to move the decimal point until you get it following the first significant non-digit zero. When you move that decimal point, you have to be counting how many times you move it. So basically what we're going to be doing when we move the decimal point is dividing or multiplying by a factor of 10. How many times we move it determines what 10 is raised to multiply it. And in every single case, the value has to be the same. In other words, we should be able to go from one number to another without changing the actual value of the number. So taking our guy here, and what I want to do is represent this in scientific notation. So first step is just to write it like this, 6.24. Easy enough. One non-zero leading digit to the left of the decimal point, and now we have to multiply it by something that represents all the zeros. So starting here, the original location for the decimal point, I move to the left 18 times to get over here. So the representation would be 6.24 times 10 raised to the 18th power electrons. When we move to the left, we end up with a positive exponent. And we'll see other examples about that a little bit later. So as you can see, to write this down, 6.24 times 10 to the 18th is straightforward. And realistically, if you want to do some calculations on this, you don't want to enter that into a calculator. Not that you could anyway. So calculators have entries that permit us to use scientific notation, or ideally in our case, being electrical people, engineering notation, which is really pretty easy. So we're going to be starting hard and getting easier as we work through this. So let's say that we have, this is just another example, 10,542 living in Rome, Ohio. That is here, and that number is very large. We want to convert this to scientific notation, so the first thing I do is write it in scientific notation form, 1.0542, and then I have to raise it 10 to a power to represent this. So again, I'm going to have my decimal point here. I'm going to be moving it 4 places to the left, and that means I'm going to have a positive exponent 4. So calculators normally have 3 modes, and you need to be familiar with all 3 of them. One is the normal mode for normal people, which we aren't. Then there's scientific notation mode, and then there's engineering notation mode, which really makes our life simpler. So I'm going to work through the scientific notation mode first, and then we'll talk about the engineering notation mode. Now, in a calculator, if I wanted to enter this, there's actually a couple ways of doing it. And one would be to enter the number 1.0542 times 10, and then you have some key to raise it to a power. In my calculator, it's a caret 4, and that would give us, in this case, if my calculator were in normal mode and I entered it this way and I hit enter, it would actually produce the original mode. But notice the entry form for this, and that's going to be made easier in a minute because calculators are designed for this because people use it many times. And we're making 1, 2, 3, 4 entries, and realistically we're going to reduce that to 2. So by setting a calculator to different modes, say I'm starting in normal mode, and I enter a number, and I want to convert that to scientific notation, I just go into mode, select scientific notation, hit enter. Done. If I want to see it in engineering notation, I just go into mode, select engineering notation, hit enter, done. So you can switch back and forth between the two, and this makes for good check values if you're doing homework. So another example, and this just happened here, is I had a remote control ceiling fan, and it has this little bitty tiny 12-volt battery in them, and they're not too cheap. And it lasts about 2 months and die, and we hardly ever changed the fan settings and couldn't understand that. So after the second time, I figured I'd start to take a look at it. So what I did is I came down here and put that under some instrumentation and found out that this current was flowing. As you can see here, there's a lot of leading zeros. It's a very small current. However, if you're dealing with a very small battery with a limited amount of energy, over a period of time, it'll drain it, because batteries store chemical energy. And what's this being used for? And the answer is it's running a little controller inside the fan remote control that scans the keyboard. If you push a button, it knows what that is, and it lights up the RF, the radio frequency component of that, transmits the information to the fan, say, to change speed. But this very small amount of current over a period of time did in the battery. So what I want to do is convert this to scientific notation, so I'm simply going to write down 4.2. I don't have to think much about that. And then take the decimal point, which would be here, and move it to the right 1, 2, 3, 4, 5, 6, 7, 8 times. Count that right? No, 7 times. And then I write that times 10 to the negative 7th power. So when I'm moving the decimal point to the right, it's going to be a negative power. If I move it to the left, it's going to be a positive power. And then we're going to take a look at this in a minute and break it down into something which is a little bit more comfortable. So that's the first thing. Right means a negative power, left means a positive power. Oh, and what I did to fix that is I took it apart and I found the printed circuit lead where the battery connects to the electronics, and I cut it. And I soldered 2 wires on that, brought it out to the top of the remote control, and glued a little push button on it. So if you want to change the fan speed, hold down this push button and then engage the speed control buttons, whatever. So when it's off, the current drain is, for all practical purposes, 0. And I haven't replaced the battery since. Okay, let's talk about the law of exponents real easy, because 10 to the negative 7th can look pretty intimidating. And what the law of exponents says is that if this is going to be in the numerator, and for your mind's eye, what I'd like you to do is think about this as 10 to the 7th divided by 1, which of course does not change anything. We can represent that as a positive exponent if we move it into the denominator. So this is mathematically equivalent to this form. So if you're a little bit bothered by negative exponents, in your mind just think it's just basically dividing by 10 raised to the 7th power. Now, this is a lot of work entering this enter exponent stuff, so let's take a look at the way we want to do it on a calculator. It's certainly not times 10 raised to a power. 4.2 times 10 to the negative 7 is what we would do on a calculator keyboard. I'm talking about a scientific calculator. Is enter 4.2, and you have a key there, either E or EE, depends on your calculator, negative 7. And what the E stands for in this case is 10 raised to. So you do not have to enter 10 in the caret to do anything. It's just, why is it here? Because this is such a common operation, they dedicated a key to it. Now, when you do this, you have to note this is not the negative subtract, this is not the subtract sign, it's the change sign. So if you put the subtract symbol there, it's going to give you an incorrect answer. If you use the change sign symbol, it'll give you the positive answer. What's the difference? Subtract is a binary operator. You have a number on this side, a number on that side, and the subtract says you're going to do something with the 2 numbers. The change sign is a unary operator, meaning all it's doing is telling you that's a negative number. It doesn't mean that anything is sitting in front of it, it's just saying it's negative. So as you can see, by putting a subtract symbol there, what is E minus 7? What does that mean? It doesn't mean anything, and it'll flag a calculator error. Okay, note, now these are not in scientific notation form, because here we have 2 digits to the left of the decimal point, and here we have a leading 0 to the left of the decimal point. So all these numbers are valid, and you can certainly work with them. There's no reason why you can't. They're not in scientific notation. So say you're taking a test and the instructor wants you to have an answer in SN. You have to have it in the right form, which is 1 non-zero digit to the left of the decimal point. Now, to make our life a little more easier, we have SI prefixes, and what they are abbreviations that represent 10 raised to some power. And these are coming to use in normal society here. For example, I didn't go any further here, but the next guy would be tera. I have a terabyte hard drive. Now, people don't know that that's going to mean 10 raised to the 12th power, and they really don't care. All they need to know is it's pretty big, and they should have some idea, based on past usage, if it's enough for their computer. So what we do with numbers here is we use these postscripts to indicate a power of 10. So let's just walk through these for a minute, and do note that these are all divisible by a factor of 3, and that's super important, because if we're in engineering notation, it'll always give us a number that's raised to, or a power rather, number that's raised to a power that's divisible by 3, which means it's very easy to pop the prefix next to it. It is a prefix. I call it postfix because it follows it, but whatever. So working through this, we have pico, and that's equal to 10 to the negative 12th, and the symbol for that is a lowercase p. Now, why ever would we be dealing with something that small? And the example is when we tune in a radio, sometimes we have to trim our capacitors with very, very low values of things to get, say, the station to be right on. Now, I'm talking about older technology when I gave you that example. Nano is a very common value for capacitors. The unit would be nanofarad, and that would be 10 to the negative 9th, and its indicator there is lowercase n. Micro is very common. I have in power supply a 2,000 microfarad capacitor, so it would be 2,000 times 10 to the negative 6, and this is the mu symbol, the Greek mu symbol. It's like a U, and the lowercase u is used many times for it. Milli is very common, lowercase m on that, and the case does matter. So a milliampere would be 1/1000th of an ampere. And to put that in perspective, if you pop a GFCI, say you're standing in water and you do something wrong, the kickout's about 8 milliamperes that, well, saves your life. After milli, we go to kilo, which means thousands, lowercase k in that case. Mega, 10 to the 6, means millions, 2 megohms, and finally we have giga, 10 to the 9th, which is uppercase G rather, and an example would be your microwave oven operates at approximately 2.45 gigahertz. That means that many cycles of operation times 2.45 per second. And think of a cycle as a pendulum swinging once back and forth. It makes a sine wave. So if we use these here, we represent all of this exponent stuff, and we can talk in a language without plugging everything up with raised to the power. And that's what we do in electronics. All we use is this stuff. It's just very convenient, and once you get used to it, it's just like learning a very, very easy second language. So it's important to become familiar with this. Now, any time that you're doing calculations, be sure you're in engineering notation, because an instructor's not going to want to see an answer 4.9 times 10 to the 4th power. That doesn't mean anything to me. That means I got to convert that answer to find out if it's correct. So always use engineering notation, and the prefix 5.8 kiloohms, 2.9 nanofarads. So you're right on track with the language of the industry, because that's what you're going to work, and the industry does not use 10 raised to the power anywhere. So in engineering notation, the decimal point never has to be moved when it comes out of a calculator. It's always going to give you an exponent that's divisible by 3, so you can quickly assign it the SI prefix. Anytime you move a decimal point, you're likely to make an error. So avoid all possibilities, make errors whenever you can, because, well, people get tired. So that's the nice thing, is it gives you an exponent that's a factor of 3, is you can immediately assign it the prefix, and then you'll be all set. In engineering notation form, however, we can have as many as 1, 2, or 3 digits to the left of a decimal point. For example, 342 kilo, let me make a lowercase k here, ohms. That's a legal engineering notation form. 42, say, milli amperes. That's a legal engineering notation form. So it's not quite as rigid before. In engineering notation, you'll never see a leading zero. There'll always be at least one significant digit to the left of the decimal point. So the leading guy here cannot be 0. So from our previous example, the fan drew 4.2 times 10 to the negative 7 amperes, and remember that would be electrons, well, multiply that by the 6.28 e to the 18th, that would be the number of electrons per second that that battery is being drained of. And if we were to convert that into notation here, that could, in engineering notation, be 420 e to the negative 9th, which equals 420 nanoamperes. Now certainly dealing with 420 nanoamperes is much preferred to dealing with the other form that we had up there, the 0.000 and so on. And using this here, you see that we don't even get into decimal point changes. Don't have to worry about it. We just look at the exponent in engineering notation, assign the prefix, equals, done. Ohm's law example. Calculate an E in the engineering mode, so it's just saying that you put your calculator in that mode. Our equation here for Ohm's law is the voltage equals the current times the resistance, and the voltage sometimes is represented by uppercase E. And in our little circuit here we have 22 volts with a sign polarity, a resistor, and a light emitting diode. And what I'm going to tell you about this is the light emitting diode is perfect for this example, meaning that the voltage drop across it is 0. And through this here, what we want to do is figure out what the current flow will be. Plus and minus means that conventional current, not electron current, flows out of the positive terminal, which is the source, through the resistor, through the diode. These are said to be in series. Lights the diode, and the purpose of this resistor is to set the current so we don't burn this guy up. So diodes, light emitting diodes, so any diode is sensitive on overcurrent situations. So the solution of this, if we divide it, is that, and what we want to do is find out what R is. And here's our equation here, V equals I times R, and what we want to do is solve for R, so we'll mathematically isolate R, and it would be equal to the voltage divided by the current. So that would be 22 divided by 1.5 enter exponent negative 3. And that would be divided by, let me think here, 22 divided by our current. Yeah, let me say, making this hard. 1.5 enter exponent negative 3. And what that produces here is a resistance value of 14.6 repeat e to the 3 ohms. In other words, R equals 14.6 repeat kiloohms. So, in your answer here, when you look at this, you write down that. Don't think about it. You just E3 kilo, done. Always have the unit. That can hurt you in grading points if you don't have it. So that's a practical thought about this, and then we're going to make a little bit more sense of this later too. This 1.5 enter exponent negative 3. You may have an option of doing something a little simpler than that, depending on how comfortable you are with the numbers. Adding and subtracting, and this is done by hand because in a calculator it's just going to handle things for you anyway. So when we add and subtract, the exponent has to be the same. So in this example here we have 4.28 times 10 to the third plus 6.45 10 to the second. And there's two ways we can get the exponent to be the same. We can either take the add-in and convert it to an exponent of 10 to the 3 and add it, or we can take our guy here and convert it to an exponent of 10 to 2 and add it. Both will give us exactly the right numbers. So in converting this to 10 to the 3, I'm going to shift the decimal point one place to the left. Gives me 10 to the 3. Add the numbers. Exponent's always going to be the same as these guys. Always. If we elect to change the top guy, we'll move the decimal point one place to the right, reduce the exponent by 1, 42.8 times 10 to the second, add them together, which gives us 49.25 times 10 to the second. Again, the exponent here is the same as these guys. Now, neither one of these, well, this is in scientific notation. This one is not. I could convert it, but we know how to do that, so I won't waste your time to do that. So that's adding and subtracting, and this is an always thing. It's not an occasional thing. The exponents have to be the same. Now, multiplying, what we're going to do is multiply the mantissa, new word. What that represents is this guy here, and we add the exponent. So let's take a little example of that. Here we have 4.28 times 10 to the third multiplied by 6.45, 10 to the second. So the first thing we're going to do is multiply these two numbers together right here. And that'll give us 27.606. And then we're going to add the exponents, and I'm going to do that explicitly here. 3 plus 2 is 10 to the fifth. So that would be the answer to that. Another example here would be 9.25 times 10 to the third. That number times 3.2 times 10 to the negative 9. So we're going to multiply the numbers, the mantissas, subtract the exponents. Now I'm being very careful here on the exponent subtraction. This guy was straightforward. Since in multiplying, when we multiply, we add the exponent. I have 3. That's an addition sign, positive sign, and the number I'm adding to it is negative 9. So the negative is the unary operator giving the sign of 9. When I have 3 plus negative 9, I'm going to be going to the left on the number line, and what we end up with is a negative 6. So the answer to that would be 29.6 times 10 to the negative 6. And remember, that's just the same as saying 29.6 divided by 10 to the positive 6. And all this means realistically is you're going to be shifting the decimal point in a normal mode this way 6 digits. In example 3, we have 25.9 raised to the 4th power times the number 5.4. Okay. 25.9 times 10 to the 4th times, and this is kind of what I want to point out here, this guy. 5.4 doesn't have an exponent, so we can multiply it by 10 raised to the 0 power. Anything raised to the 0 power except 0 is going to be 1, so we don't change anything. Following the rules then is what we end up with. An answer is 1.399, and what we have is 10 to the 4th. Oh, I'm sorry, 4 times 0. Love this on the fly stuff. Adding those together would be 4 plus 0 would be 10 to the 4th power. So if you're dealing with a number that doesn't have an exponent in your mind's eye, if you want to, you can picture it as being multiplied by 10 raised to the 0 power, and then follow the rules. Again, you multiply the numbers, and you add the exponents, being very careful of the signs. Now, division, as you might suspect, things are going to be a little bit different. Divide the numbers, and these would be the mantissas again, and then for the exponents, what we do is we subtract the exponent in the denominator from the exponent in the numerator. So an example of that would be 5.3 times 10 to the third divided by 6.92 times 10 to the negative fifth. So the first part of this is we're simply going to divide the numbers here together and enter that. Now we're taking 3, positive 3, and subtracting from it a negative 5. Again, note the careful breakdown of this. So what the rules say when you're adding, like this here, is you, when you're subtracting rather, is you change the sign of what you're subtracting and add. So this negative 5 would become plus 5, and you're going to add 3 to 5, which is going to give you 8. So when you're dealing with this sort of thing, it's best just not to do it in your head. You know, write it down with the binary operator subtract and the sign, unless it's really an easy number, and then follow the rules for subtracting sign numbers. Change the sign of the subtrahend and add. That's the rule. Equation number 2, and these are not in scientific notation, I made a little note for myself there, would be 10.3 raised to the negative third divided by 5.8 times 10 squared. Again, divide the numbers. It's that guy. In the exponents here we have negative 3, because the numerator always comes first and you're subtracting from a denominator, so that would be minus a positive 2. So what the rules say about that is we have negative 3, change the sign of the subtrahend, making it negative 2, and add. So that would give us a new exponent here of negative 5. Finally, we have 25, regular number here, times 10 to the 0 power, actually is what we're going to do with it, divided by 3.9 times 10 to the third. So dividing the numbers as before gives us this, and now I have 0 in the numerator minus a positive 3 in the denominator, which gives us an answer of 6.41 times 10 to the negative third power. So those are the rules for division. You subtract the exponent in the denominator from that of the numerator, being super careful of the signs. So if you get those wrong, well, your answer's off by a lot. Okay, common sense. Is there an easier, faster way to do this? Yeah, there is. So let's take a look at this. Voltage equals current times resistance, our basic Ohm's law formula. And suppose we have a 5.2 megohm resistor, and just for reference I've written that down in engineering notation here, I guess engineering notation, 5.2 e to the 6th ohms. So you can correlate this if you're not quite familiar with uppercase M. We have 25 milliamperes flowing through it, so that would be 25 e to the negative third. So on your calculator, if you want to enter 5.2 e to the 6th power, and what we're going to be doing is multiplying these together, times 25 e negative 3, that's perfectly fine. In a calculator, it doesn't matter whether the exponents are the same or different or whatever. There's no restrictions on that. They're smart enough to figure it out. Now maybe, since I don't want to put in a bunch of zeros, I like to add this as 5.2 e to the 6th in my calculator. It'd be easier for me to punch in a calculator .025. I don't have to put it in this form. If this is easier for me to do, do it. End up with the same answer. Another example would be a 25K resistor, and flowing through that's going to be 920 nanoamperes. So realistically, I don't want to put 6 zeros in front of the 9 here with a decimal point to represent nanoamperes. So entering this in this form makes sense. Multiplying it by 25K, on the other hand, I could use 25 e to the 3. However, on the calculator keypad, 25 hitting zeros 3 times is probably faster. What do you want to do? What's easiest for you? What you don't want to do is make a mistake. So that'll conclude, and if this seems kind of foreign, what I'll say to you is that as you work with this, and especially with your calculators in engineering mode, you get used to it. It just becomes second nature. It's very easy. I've seen students in third semester classes using scientific notation, and I tell them about engineering notation with a big question mark. Why don't you? And they say, oh, that's easy. And I don't know how they missed it, but whatever. So that'll conclude, and thank you for watching.